Alright guys, welcome to this page of the notes, and here's what we're going to do. I'm actually going to have you work the opposite direction, and this is not the first time we've seen this. I had you do this in chapter 4 as well for quadratic functions. And what we're going to do is I'm going to give you the roots of the polynomial. I'll tell you what the x-intercepts are, and then ask you to write the polynomial that has those x-intercepts. I did the exact same thing for you guys in quadratics, where I gave you the roots and asked you to write the quadratic. You may remember this formula. We're actually going to use the exact same formula, and it's this. F of x, actually, you know what? Here, let's call it p of x because it's a polynomial. P of x is equal to x minus p times x minus q, where p and q were the roots of the quadratic formula, right? So whatever roots I gave you, like if I told you the quadratic crosses the x-axis at -2 and +3, then you would plug a -2 in for p, a +3 in for q, FOIL this out, and you get your quadratic. We're going to do the exact same thing here, except because they're polynomials, you may have more than 2 roots, which means we just need to add as many terms as you need. So let's go ahead and add another one. Maybe I'm going to need an x minus v and an x minus z, ... right? However many factors you need, depending on the number of roots I've given you, and we'll just multiply all these guys together to get our polynomial. P, Q, V, Z, whatever letters you want to call them, that's where you're going to plug in the roots that I give you in the problem. Now, the reason we just talked about complex conjugates is because I am going to try and trip you up. Not purposefully, but I'm testing you to see if you remember imaginary solutions come as complex conjugates. So here's how I'm going to do that. If you know that imaginary solutions come as complex conjugates, if an imaginary number is a 0, you know the complex conjugate must also be a 0 for that function or polynomial. So here we go. Let's jump right into this example problem, and I'm show you how I'm going to test you on this. What you're going to do is I've asked you to write a polynomial function, least degree, that'll all come out. Integral coefficients, that just means you're going to have numbers as your coefficients. We don't want fractions, so if you wind up with a fraction as a coefficient, you'll need to multiply everybody by the denominator to get rid of the fractions. You're used to doing that as well. We want these in standard form. And here's what I tell you. The zeros of the polynomial I'm looking for are -1 and 5 minus I. Now, 5 minus I is an imaginary solution, 5 minus I. But you know that they must come as complex conjugates, which means 5 plus I, the complex conjugate, must also be a 0. So here you go. You have x equals -1, 5 minus I, and 5 plus I as your zeros, thanks to the complex conjugate theorem, which says that if one imaginary solution, if one imaginary number is a solution to a polynomial, its complex conjugate must also be a solution to that polynomial. So I have 3 zeros, and we're going to go ahead and use this formula to find that polynomial. So here we go. My polynomial, p of x, is going to be equal to, p of x is going to be equal to x minus p. My first 0 is a -1, so I'll have x minus a -1. Okay, that's my first one. My next one is going to be x minus, and then my next 0 is 5 minus I. So x minus 5 minus I. Make sure you put parentheses in there because you'll need to distribute that minus sign. And then my last one is going to be x minus 5 plus I. All right, let's go ahead and start this off by distributing my minus signs through the parentheses to go ahead and get rid of those. So P of x is going to be equal to x plus 1, and then x minus 5 plus I, and x minus 5 minus I. Okay, now there's really no shortcut to this. You're going to have to use the distributive property to multiply all this stuff together. And I know it looks scary, but let me encourage you before we start. In these problems, all right, the i's will always drop out. It's going to be a cancellation palooza. Once you've multiplied these guys together, you're going to have a whole bunch of terms that cancel each other out. All of the i's will drop out. If you get to the end and you have a polynomial that still has an I in it, you made a mistake. Go back and figure out what you did wrong. So here we go. Let's start multiplying. I'm going to start by multiplying these guys together. So I'm going to have P of x is equal to x plus 1. And then here we go. X times x, x squared. X times a minus 5 is going to be minus 5x. And x times a minus I is going to be minus xi. Next. Negative 5 times x minus 5x. Negative 5 times negative 5 is going to be plus 25. And negative 5 times negative I is going to be plus 5i. And now the last one. Sorry about that. Stray marks. Okay, the last one is going to be I. So I'm going to have, let's see here. I times x is going to be plus xi. I apologize, I'm going to try and squeeze. I am sorry about that, I keep squeezing on you guys. I times negative 5 is going to be minus 5i, minus 5i. And then the last one, I times would be a negative I squared, minus I squared. All right, so there we go. I've got these guys all multiplied out, and here's what happens. Run through that real quick. I have a negative xi and a positive xi. Those drop out. I have a plus 5i and a minus 5i. Those drop out. And then the last thing, you have a negative I squared. Well, hopefully what you guys remember from chapter 4, and if you don't, I'll write it right here. Remember, I is equal to the square root of negative 1, and I squared is equal to negative 1. Well, I have a minus I squared. Well, I squared is equal to a negative 1, right? That's what I squared is equal to. It's equal to a negative 1, and negative 1 and negative 1 is a positive 1. So I'll just add that to the 25, and that'll actually give me a 26. So here's what that whole thing boils down to. X squared minus 5x is going to be minus 10x. And then positive 25, positive 1, plus 26. All right, last thing you need to do is just multiply these guys together and you will have your polynomial. Okay, x times x is x cubed. X times negative 10x minus 10x squared. X times plus 26 will be plus 26x. And then I'm going to have a plus x squared minus 10x and plus 26. Combine all of my like terms, x cubed minus 10x plus x squared should give me a minus 9x squared. Positive 26x minus 10x should be a positive 16x. And then plus 26. All of my coefficients are integers, 1, minus 9, 16, 26. I don't have any fractions, so I don't have to worry about multiplying this polynomial by a denominator. That is your polynomial of lowest degree, third degree, because I had 3 zeros. Negative 1, 5 minus I, and 5 plus I, 3 zeros. Third degree, fundamental theorem of algebra holds true, right? We don't want to break the fundamental theorem of algebra. Don't do that. So lowest degree, integer coefficients, and you've got yourself your polynomial. All right, again, it's just a whole bunch of foiling and going back to what we did in chapter 4 with quadratics, just a little bit more complicated because you're going to have more zeros. But we'll try another one. So head on over to the next page of the notes. We'll look at another example problem, and I'll meet you guys there.